Hi, welcome to the course Machine Learning with Python. This course is distributed across 5 modules, and this is the first module. In this module, we'll have a general introduction to the topic. Let's get started. Let's understand what are the content that we will be covering in this module. To start with the bigger picture, we understand why did the field of data science come into existence. Once we have a fair amount of understanding of the bigger picture, we look at the problem landscape. We'll try and explore and understand what are the problems that the industry is trying to solve, which eventually led to the rise of the field of data science. With a good amount of understanding about the background of data science and about how it evolved, we'll try to take a shot at formally defining data science. Though there is no formal definition, we'll take a shot at defining data science in the most layman language. Now, if you have ever explored data science earlier, you have definitely come across various ambiguous terms like decision science, artificial intelligence, machine learning, deep learning, and many more. It's very difficult to understand how are they different and how are they connected. So once we have fair amount of understanding about data science, we'll take a shot at understanding how are they different, how are these ambiguous terms connected, and how are they different. Finally, we'll explore the data scientist toolbox. You have definitely come across languages like R, Python, Vika, SAS, and many more. It's important to understand which one to choose. What does one language or one technology offer compared to the other? In this course, we'll be using Python, so it's important to understand why did we choose Python? What are the advantages of Python? And so on. We'll get in the details of these sections one by one. So let's get started. So let us understand the bigger picture. So how did it start? Why did the field of data science actually come into existence? To answer it in a very simple line, I would say it all starts with decision making and business strategy. So in the early era, like the early 1900s, 1900 to 1950, that was a time when majority of the industries, organizations lacked the digital infrastructure for obvious reasons. So historically, business strategies and decisions were backed by intuitions, experiences, and heuristics. Research was very limited. The reason for research being very limited is because research was actually very expensive. We'll try to illustrate this entire concept in this simple graph. The y-axis over here is actually an indicator of data-driven decisions maturity. What is the maturity of data-driven decisions? And the x-axis over here is a timeline of till the present day. So before digitization can be termed as, let's say, 1900 to 1960 or 1970. 1970 was the time when digital adoption slowly came into existence. And then till around 95 to 98 or probably early 2000, that was the time when most of the enterprises embraced the digital adoption. Post that, I would say till the present day, like the last 15-20 years, is a time when we have a data explosion. Like vast volumes of data have been collected, computing power is more cost effective, and so on. So we are presently over here. This is the last 20 years, or probably 25 years. This is around 1975 to 1995, around 20 years. And this is the era before that. So as time evolved, digital adoption was in place and data was readily available. And naturally, a field, business intelligence, that was born. So what happens over here is there's an organization, they want to take a new business decision or probably new strategy for probably a defined outcome. So let's say they want to increase their revenue. So how do they increase their revenue? They'll have a couple of business questions and they need answers to those questions. That's when you have intuitions, experiences, heuristics in place. So the early era primarily primarily depended on heuristics and experiences. Research was very expensive over here. You had to literally go through the numbers manually, calculate them. There's a lot of man-hours required over here. Labor was intensive and expensive. So the kind of decisions taken from data were very limited. Then came a time when we could actually use computers and digital data was really available. That's when business intelligence reports came into picture. So you have business questions, you need answers to business questions. You have reports, you have programs that have been written, which can actually extract data, process data, and transform data into insights. Now this process was fairly simple because the kind of, or the volume of data which we had in this era was also small. Like if you compare the data with the size of data which we have today, this would almost be zero. Then came a time where the volume of data increased. So when the volume of data increased, the kind of answers that you could actually get also increased, or also the quality of the answers also increased. So, and this process of getting insights from data is very addictive. Like the moment you have answered one of the questions, there are probably a couple of more follow-up questions. This is a very addictive process. So business started depending on data heavily. So this transition, that is from BI first generation to second generation, and then eventually to the third generation, the present day's artificial intelligence, actually happened very fast. And the process actually became very complex. That's when data science was born. So BI was actually in place for a couple of decades. And the process was very straightforward. You had sufficient amount of data. There was a structured approach to approach the data, use the data for generating insights, and so on. But as data exploded in the present day, the process of extracting insights from data is a fairly complex process, and we can't just rely on the traditional methods that we used. And today, we just don't have data-driven decisions. We actually build data products. And that's when the entire field of data science came into picture. So to formally define, I would say data science is that art which deals with the complex process of deriving insights from data. When you compare the present day's complexity with around the complexity around 20 years back, there's a huge difference. And that difference was primarily driven by the volume and the availability of data. So the takeaway from this slide, that is the bigger picture, we would say that data science as a field all started with decision making and business strategy. You have questions, you need answers, and that's a very addictive game. In that process, you try to capture more and more data, and you try to and the organizations present at that point of time try to extract more and more insights from the available data. And that process, the entire process got complicated. That's when a new field in itself was born. And that is what we call today data science. So data science, I would say, is an umbrella to all the terms that we have heard till now, like machine learning, artificial intelligence, data analysis, all of them, and in fact even business intelligence. All of these terms can be combined together to form a larger umbrella called data science. Let's move on. So let's take a look at the problem landscape. Basically, we'll try to understand what kind of problems did the industry try to solve, which eventually led to the rise of data science and machine learning. So in the previous slide, we learned that the root or the crux of data science actually came from business strategy and decision making. So while this happens, so when any organization is in the process of making a decision or implementing a business strategy, they actually try to solve a problem. So to understand the nature of the problems that actually evolved into data science, let's understand the crux of problem with more depth. So let's look at this representation over here. What we have done over here is we have tried to define problems using two dimensions. One is impact and one is frequency. A problem could actually have low or high impact, and the frequency could also be low and high. So based on these two dimensions, we can actually segregate the problems into these four quadrants, like low impact and low frequency, high frequency and low impact. Similarly, high impact, high frequency, and high impact, low frequency. So if you take a look at these problems in these four quadrants, we'll actually understand problems from a different angle. So let's understand this better. What kind of problems actually come over here? So low impact, low frequency. This is that segment which is actually not that important because the frequency of the problems is not so high and the impact is also so low. So it's okay to adjust with it. Organizations don't really bother to solve these problems. Then there are a couple of problems where the impact is not so high, it's low. and the frequency is so high that it becomes bottleneck. This is where we have the industry of IT solutions into the picture. So today, if you look into the IT solutions developed by major service companies, let's say Infosys, TCS, major outsourcing companies, we all focus in this area where you try to solve a problem where the impact is not very high, but the frequency is extremely high. So it actually makes sense to digitize a solution and permanently fix it. One common example over here would be a customer relationship portal, or let's say digitizing the inventory system. So let's say if a company has a digitized supply chain or an inventory management system, if it goes on for a day, the impact is not going to be terrible. It's going to be okay. But then once it's digitized, once the problem is solved, the frequency of this happening again and again, the frequency at which the problem comes again, inventory problems have to be updated, that's very high. This understanding gets better as we look into the other quadrants. So let's say what could be an example over here? Extremely high impact, but very low frequency. This could be as simple as, should I take the company public or not? Or should I sell the company? Or should I merge with this company? Or should I acquire this company? Should I sell my IP? These questions and these business decisions, the frequency is very low. It might happen actually once in a lifetime of a company, or probably once or twice in a year. So since the frequency is very low and the impact being extremely high, companies generally tend to spend more over here. Like it's okay if you spend a little high in this segment. So to solve these problems, like we have a couple of different industries called the consulting industry. So McKinsey, Booz Allen Hamilton, A.T. Kearney, Boston Consulting Group, all these consulting companies, they actually come into the picture when we have extremely high impact and low frequency problems. And then we have an altogether different game, like extremely high impact problems and extremely high frequency problems. A simple example would be the page ranking algorithm of Google. Like the impact is extremely huge and the frequency is also very, very high. Like you need to come up with an extremely robust and very powerful and more accurate version every day. Another simple example would be the pricing problem. Let's say for an e-commerce giant like Amazon or Flipkart in India, pricing of the products is something which is extremely sensitive and has an extremely huge impact. And the frequency is also very high. You have almost every day some new pricing technique coming into picture. The price changes for the product on a very frequent basis. So the idea behind dividing problems into these 4 quadrants are the way we approach these problems in these quadrants are actually different. So for example, let's take this bucket, low impact and low frequency. This could be something as trivial as an HR solution or a couple of people policies within the company where it's okay to delay it, or it's okay to probably, my apologies, not necessarily HR problems are always low impact and low frequency, but then, these are those problems that the companies are generally not interested to solve. So let's ignore this bucket. Extremely high impact, extremely low frequency, it's okay to spend a little more, and companies like consulting come into the picture. Here, the approach to solve this problem is more heuristic driven, right? Similarly, if you take into account this segment, low impact, the frequency is very high. Like it may happen on a very high scale basis. You need to actually solve it very algorithmically. So as you move from low to high on the impact and low to high on frequency, here you tend to solve the problem more algorithmically, and here you tend to solve the problem more heuristically. The problem comes over here when you have extremely high impact and extremely high frequency. It's a combination of several things. So this is altogether a different ballgame. Let's ignore this for now. Let's focus on these 2 areas. So what happens is, in each of these quadrants, there are again 2 subsections, probably, we have a section where you have extremely high impact, extremely low frequency, but then again, there is a scope to divide them into 2, where there is a small difference between this segment and this segment. The same happens over here. Now, coming back to the crux, let's come back to the first question. How is data science connected over here? So, as I mentioned, as we move from low to high impact, we move into a very heuristic approach. As we move from low to high frequency, we move into a very algorithmic approach. When these two converge together, we have a different set of interesting problems that we solve, and that is highlighted over here. It's extremely complex, it's extremely ambiguous, and it's extremely connected. You don't really have a structure to these problems. So what happens is generally a company starts solving somewhere in this section where it's moderately low impact and moderately low frequency. But the moment they try to solve this problem, they understand that, okay, we actually need to solve a problem which is connected to this and it is belonging to this domain. And similarly, something over here would be connected over here. Something over here would be connected over here. So the approach is very muddy. You'll have to do a lot of exploration to actually understand what is the structure of the problem. And that's when data comes into picture, because you have a lot of questions. These questions need answers, and then you have data-driven decision making. Now, this entire concept might sound very abstract. Let's take a very tangible example to understand how do problems actually fit in these different segments. So let's say someone like Amazon is trying to solve the problem of pricing. So they plan to solve the problem of pricing by implementing a technique which will actually update. And for simplicity, let's assume that we have just one product in the entire catalog. Let's say the product is mobile phones. So Apple launches a new iPhone is in the market. Amazon is actually implementing a pricing technique that will set up a new price point almost every day to have maximum sales. This is probably a very abstract problem, but then still let's take into account something that a company is trying to solve for the first time. Now, when they try to solve this problem, they'll actually understand, okay, before solving this problem, probably I'll need to actually have an entire digitized version of my catalog system, of my supply chain, of my inventory. So that's a problem which comes in this section. The impact is low, but the frequency is very high. And that is connected to a problem which comes in this segment. So they would actually go ahead, digitize the entire solution, get a solution in place where everything is connected to each other. We have one centralized database where all the inventory and management is done with a digital sense. All of that is done. And when one small problem is solved, they actually understand there's something more important that we need to solve over here. And that might be connected to a high impact, low frequency area. And this goes on. So what happens is this area that is a rectangle which touches all these four quadrants in a small way defines those set of interesting problems which lack a particular structure. You don't really have a standard protocol to solve these problems. It's a very exploratory approach. And these are the problems which actually led to the field of data science. So what happened is, you're trying to solve a problem, then you understand this problem is actually connected to another problem. It's extremely high impact, low frequency, it's an extremely ambiguous scenario. Now, to solve a problem in this segment, you don't have an approach. So you go a very exploratory way. And then in this process, you'll have a lot of questions. These questions again need a lot of answers. And in that process, you actually leverage data. Mostly it's a data-driven decision that you take. And this process gets complicated because the scale of the complexity increases as the impact increases for the problem. And in that process, we actually created an art, a new field emerged, that is data science. Machine learning is a smaller segment in this entire picture. We'll get into the depth of machine learning very soon. But connecting the previous slide to the problem landscape, we are trying to understand what kind of problems did the industry solve, which eventually led to the rise of this field, data science. So let's take into account the next section. Now that we have a fair amount of background about the field of data science and how it came into existence, let's take a shot at formally defining data science. Now, this is a complicated process because there's actually no formal definition for data science. If you Google the topic, you'll actually come across several of them, and probably all of them will be right. It's actually a long debate to understand which will be the best one. So let's take a shot at giving the most layman explanation for the field of data science. In the simplest term, data science can be defined as the art and science of making data-driven decisions. This may sound a little fancy, but then let's understand the crux behind it. The process of making data-driven decisions is actually a little complicated. Now, if there's an art, if we understand that complexity, we can actually make it less complicated. So the process of making data-driven decisions in a relatively structured way can be defined as data science. But this field is actually very interdisciplinary and requires a combination of skills that have never been leveraged in the industry together. We'll actually take a deeper look at this once we come back to by understanding what are these skill sets. So it's a combination of primarily three skills: math, business, and technology. Math could be statistics, linear algebra, probability, and many more. Business is actually the domain knowledge of that system. So for example, let's say you're trying to solve a problem for an e-commerce giant like Amazon. So profound knowledge of the e-commerce industry is actually important to understand before we try to solve the problem. And lastly, technology. This is basically programming and hacking skills. It could be any technology skills like C, C++, Java, Python, R, or many more. We'll get into the depth of what technology do we use here specifically very soon. Now, the modern definition for data science actually adds in several more new skills apart from math, business, and technology. So, design thinking, behavioral science, cognitive intelligence, and many more. Thus, it actually becomes a truly interdisciplinary skill field. Let's understand this in a little depth. So initially, we had the industry which was primarily banking on a combination of two skill sets. It could be any of them. So let's say if we take into account math, business, and technology, math and business together created the consulting industry. So McKinsey, Booz Allen Hamilton, A.T. Kearney, all these large consulting companies which we came across in the last slide actually solved the problem by combining business and math. And that is the reason why they actually solved problems in a very heuristic approach way. We then have a combination of business and technology. So companies like Infosys, TCS, Cognizant. These are companies who are typically known for their IT services. And they actually solve a specific problem by combining business and technology together. Technically, if you look at the previous slide, it actually refers to the high frequency and low impact area. Finally, we have companies who solve math and technology skills together. So these are companies which create amazing products. Adobe, NVIDIA, and so many more. So Adobe Photoshop is actually a simple example to understand skills of math and technology being combined together. There's definitely a lot more, but then primarily we have math and technology over there. But then when we have these three skill sets together, math, business, and technology, that's the area where magic is created, and we call that data science. It's definitely interdisciplinary, and with today's definition, it's truly interdisciplinary. Now, as you come across the term data science, you'll actually understand a lot of different terms that are associated with data science. A couple of them actually are referred over here. You come across terms like natural language processing, decision science, neural networks, deep learning, data mining, data analysis, and probably many more. These are just a couple of them. The list is a long one. We'll take a look at understanding how are they organized. In a simplest way, data science, since we define this as the process of, as the art and science of making data-driven decisions, data science will be the larger umbrella which covers everything. Within data science, we have this important and significant field of artificial intelligence, which got very popular in recent years. Machine learning is actually a subfield within artificial intelligence. And deep learning is analogous to the modern neural networks or the cool stuff which we see in chatbots, Siri in iPhone, Google now on Android, and so on. All that cool stuff, self-driving cars, all those cool stuff happen over here, which is deep learning. Deep learning is actually a subfield within machine learning. Now, this entire process needs a couple of other elements to process and tailor data. And that's when we have data plumbing, data engineering, data visualization, data wrangling. Data plumbing is, in a nutshell, defined as sourcing and pipelining data into a source required for the process. So you'll have data across several different locations. You need to plumb them together, just like you plumb for a water resource, and then put them together in a way that they start a process, flow, and reach the destination as and when required. Like you plumb the process. Once the data is plumbed, you actually clean, process, transform the data to a more usable format. In a nutshell, it's called data engineering. You need to understand the data, so you visualize the data. You have several ways to go and visualize the data. Once you visualize the data, you probably need to make it analytical ready so that you can do some analysis on that. The process of converting data into a more analytically ready data set is actually data wrangling. A very fancy term, but then all of these together, along with AI, machine learning, and deep learning, together form data science. Let's take an additional step to actually understand data science and these associated terms in a better way. So, let's demystify data science, artificial intelligence, machine learning, and deep learning. We'll start with the simple topic and probably important one, artificial intelligence. Artificial intelligence is a branch of computer science that deals with providing intelligence to machines artificially. So basically, you have a machine which is not smart, and to make it smart, you need to embed some sort of intelligence into it. Now, embedding intelligence into a machine or a program artificially can be termed as artificial intelligence, and that's why the name artificial intelligence. Sometimes they could be as simple as simple rule-based systems, knowledge-driven databases. It could be simply a program which has a couple of if-else statements that could actually help it make some smarter decisions. So that's the field of artificial intelligence. There's definitely a lot more than simple rule-based systems, but then at a high level, any sort of intelligence that can be added to a machine artificially can be termed as the field of artificial intelligence. Machine learning has, however, a little different definition than artificial intelligence. It's definitely a process where you actually add more intelligence, but then if you take a formal shot at it, you can say a subfield within AI that deals with making machines intelligent without explicit programming. But this is the catch. So in machine learning, there is no process where you actually go ahead and hard-code rules or create a list of conditions or knowledge-driven databases. It's actually done without explicit programming. In a nutshell, the process learns on its own. And this is actually the most successful branch of AI. Now, deep learning is actually a derived field or a field within machine learning. It's a subfield of machine learning that deals with making machines intelligent and are concerned with algorithms inspired by the structure and function of the brain. So what happens is, while solving a machine learning problem, in a couple of cases, let's say like something specific to images, you're building a classification algorithm. These terms may sound a little new. We'll get into the depth in the upcoming sessions. But then just assume that you're creating a machine which actually understands when you pass an image, whether it's a cat or a dog. So machine learning could actually solve this problem, but then it becomes extremely difficult because machines, or the way we understand images are different. So we understand images in a different way, and the way computers understand images is fairly different. So the same approach which we use for traditional transactional data cannot actually be used for something as complex as image, sound, video, something like that. So there was a modern approach over there where we took inspiration of how the brain works and how the brain learns, and we've created a field called neural networks. A more successful and a modern outlook towards it was called deep learning, which is nothing but deep neural networks, which actually got a breakthrough in images, videos, and other complex data types. All of these might sound a little complicated right now, but then we'll get into the depth very soon. A combination of all of this is data science. Just like we saw in the previous slide, data science deals with the entire journey of extracting, cleaning, transforming, visualizing, mining, and developing AI, ML, artificial intelligence, or machine learning products from data. In a nutshell, you're taking data-driven decisions. So we have finally reached the last section in the first module. We'll explore the data scientist's toolbox. It's important to know what kind of tools are available for which eases the life of a data scientist while he's trying to deal with data. So what tools do you use for manipulating data, engineering data, visualizing data, creating algorithms, or probably you want to put into production a machine learning algorithm? What kind of tools and infrastructure is available? A lot of questions, right? So we'll actually take a shot at understanding what does the market offer at the present, and then what languages we'll be using in this course, and why do we use them. So towards the right hand side, this is a list of a couple of popular languages available in the market right now. R and Python are the most popular ones. We have SAS, SPSS, Julia also coming up. And Excel is a tool which actually fits in anywhere. It's extremely useful for doing quick and dirty analysis. You want to showcase or present some results to somebody else, create quick mock-ups of dashboards. Excel is probably a tool which fits in everywhere. The only trade-off over here is it's difficult to work with large amounts of data. So and one thing I wanted to point out. So today R and Python are really popular, but then a couple of years back, I would say SAS was one of the most popular languages. Today it's getting a little obsolete because R and Python are offering free alternatives than SAS. SAS was very expensive. The licensing system for SAS was very expensive. And today, only I think it's mainly popular across the banking domain. So most of the banking companies still prefer SAS. There are definitely a couple of others, but then mostly you'll see the banking companies are the ones who still use SAS. Most of the industry have actually transitioned towards R or Python, and now in fact towards Python. So in this section, we'll be using Python. Like this entire course, we'll be having the entire hands-on activity with Python. Let's take a look at understanding like why are R and Python very popular. So a little background about R. So definition-wise, R is an open source programming language and software environment for statistical computing. It's widely used by researchers and data miners. It's actually an implementation of S language. It was created by a team from Bell Labs. So S stood for statistics. It is a language which actually offered uh, most of the important algorithms and statistical techniques for researchers, academicians, and all of those PhD guys who wanted to do data analysis at a small level. It actually offered a lot of things compared to the time it was developed in. Later, a couple of folks from New Zealand in University of Auckland launched the first version in 1995, and a stable version was actually released in 2000. So the name R actually came into picture because both of the founders, Ross Ahenka and Robert Gentleman, both of their names start with R. The language, but actually got a lot of traction somewhere around the year 2005. So a scientist named Hadley Wickham was largely responsible for this revolution. He actually launched various packages that made life very easy with R. So a lot of packages around visualizing data and manipulating data is actually made possible with the packages launched by Hadley Wickham. It started with 2005 where he launched the package Reshape. Reshape was what we do in so the pivoting process in Excel is actually what we do in Reshape. So it made the process of pivoting data across dimensions extremely simple. So today, almost all libraries launched by Hadley Wickham are extremely popular and downloaded a million number of times. So almost the entire community of data science using our library package called DPLYR for data manipulation. It makes the entire process very easy. Almost everyone visualizes data using a package called ggplot. Pivoting data is completely done using the package Reshape. There's a newer version called Reshape 2, and so on. So the language got extremely popular around 2005 and got a lot of traction because it is very easy to use, and a wide and a large community was actually supporting the language. So it was very easy to get help, and then there's no better alternative at that point of time. So from 2005 onwards, R really picked up. Somewhere around the same time, Python also started picking up for data science. Like Python was also in the picture from 1991, but then it actually got traction after R's popularity. So let's take a look at Python. Python is also a very popular open source general purpose programming language. It was created around the year 1991, and majority of the data science components actually came around the year 2005. So once R started getting popularity, Python also had a community which was ready to adopt data science into the stack. So a lot of packages were developed which actually provided data science features, and they actually mimicked a lot of features right away from R. The revolution happened somewhere around 2009. 2009 is the time when Pandas was launched. So just to give you a brief context of what Pandas, so in R, the easy task of manipulating data was actually provided by data frames. Like it's something very similar to what you have in Excel. You have a tabular data format data. You can actually do row-wise operations, column-wise operations, and much more in using a couple of functions. So that entire process of visualizing data as a data frame in R was mimicked in Python using pandas. Similarly, NumPy was a set of functions that helped us do a lot of operations on an array. So you needed some array level operations. It was very easy using NumPy. Matplotlib was the visualization library, so something similar to ggplot in R. Matplotlib offered Python suite a couple of functions that could be used for visualizing the data. SciPy was a collection of statistical techniques, which was very similar to what we had in MATLAB. And another breakthrough happened with scikit-learn. Scikit-learn is actually the machine learning uh, package for Python. It's an extremely exhaustive and well organized package which actually covers the almost all the important techniques in machine learning under one roof. So a combination of all of this actually made Python a great option to explore for data science. Now, the other edge Python was more object oriented and there was a less steep learning curve compared to R. So today, if you look at the data science community, significant portion actually comes from computer science background, and computer science background guys will definitely have some sort of exposure to languages like C++ or Java. So with someone with exposure to these languages, for them to pick up Python is relatively very simple than to pick up R. So it offered a lot of other advantages also. So since Python was very popular for a lot of different software tech activities, it is very easy to take any machine learning model into a production code. So the production level support, almost the entire stack of software in the production environment had great support for Python. So that naturally made Python a preferred choice for computer engineers. So it's easy. So you can actually start from scratch, manipulate data, work with data, engineer data, visualize, create algorithms, and then finally put them into production using Python. And there's a lot of support for Python in the production environment. R on that front might be a little lower. So today, if you look into the market, we can say R is actually a language mainly used for prototyping, quick and fast prototyping. And when you actually take a machine learning model or a final product into production, Python is kind of the preferred choice. Moreover, deep learning is picking up really well in the market, and Python has a lot to offer on the front of deep learning. R also has it, but the kind of packages or different frameworks which which have been launched, Python has been a clear winner in this case. So sometime down the line, so right now we would say the community is equally divided across R and Python, but then sometime down the line I can see Python becoming a clear winner. In this course, the entire hands-on activity, including learning basic program constructs and how to handle data, building models, all of that hands-on activity will actually be covered using Python. So that's a brief introduction to the topic and the data scientist toolbox. In the next section, we'll actually explore the data scientist toolbox in more depth. So we'll actually get started with Python and understand how can we use Python to play around with data. We learn how to set up and install Python and get started with the language. So at the end of module 2, you'll have a pretty good exposure, hands-on exposure to Python, and you'll have basic understanding. So you already have basic understanding about data science and machine learning. Module 2, you'll have a basic understanding and good hands-on activity of Python, which will make us ready to get started to the main core algorithms. So that's it for now. Thank you for being so patient. Looking forward to meet you in module 2. Thank you so much.